Okay, so Dave, I'm just going to quickly go over with the stoichiometry. That's very important for the HL as well as SL students. So let's quickly look at the last part of stoichiometry, and that is the ideal gas law. Now, the ideal gas law is PV is equal to nRT. Okay, so let's quickly break it up into what is the meaning of each part of the component of this law, and then we're going to talk about where does this law come from, what is this law based on. Let's quickly first look at the components of the equation. This P stands for pressure, the V is volume, N is my number of moles, R is the gas constant, and T, and I'm sorry, actually it should be a capital T, not a small letter t, because that means time, so my mistake. T is for temperature. Capital T, because small letter t means time. So this is temperature, my mistake. So PV is equal to nRT. For each one of the components in this law, we have to have a specific unit. So you've got to make sure that when you use this gas law, that everything in the question is converted to the following units. If you are working with pressure, you need to make sure that your pressure is given as kilopascal. If it's in Pascal, for example, you need to convert it to kilopascals. Your volume has to be in decimeters cube. We can also put it in liters, because 1 liter and 1 decimeter cube is the same thing. R is your ideal gas constant. Now, for the value of 8.31 as the value of R, you have to have the pressure as kilopascal. Your temperature, yes, Saud?
8.31 kPa.
So it's just, it's 8.31 is that value. So there is a unit, we're not going to worry about the units now, but it does have a unit. It's just a constant value, which means that is the same value every time. However, when R is equal to 8.31, then your pressure has to be in kilopascals. Your temperature has to be in Kelvin. In other words, if it's given to you in degrees Celsius, you have to convert the temperature from degrees Celsius to Kelvin. So how do I convert from degrees Celsius to Kelvin? How is that done?
You add 273.
Right, so if you need to go from degrees Celsius to Kelvin, you simply add, you take your degrees Celsius and you add to it 273. That is going to tell you how many Kelvin it is. So that's all you have to do. Whatever you do is you take your degrees Celsius, you add 273 to it, and that's going to give you how many Kelvin your temperature is supposed to be. Now, where does this law come from, and what does this law actually apply to? We call it the ideal gas law. Now the name tells you that this is under ideal conditions. So if you had to have ideal conditions in the school, what would the ideal conditions be for you, Omar?
Ideal conditions for me.
What would be ideal school conditions for you? Think about the school. What would make the school ideal for you?
Better food in the cafeteria.
Better food in the cafeteria, that's a good one. Yes, what else? George, Aditya?
I don't know.
You don't know? Saud?
Desk.
You want better desks?
Yeah, exactly.
Okay, so you would like a different desk, maybe a more comfortable chair, yes?
Better organizational structure.
Oh, that's, but like how? How better?
Like not having 7 summers in a week.
Okay, so that's ideal, not having to write 7 summative exams in a week. What else would make this like the ultimate school to be in? Come on, give me something better than that.
A safe environment.
Well, it is safe.
As safe as a school gets. I haven't seen a single.
I don't think most schools here are extremely safe. So let's say, for example, during a free period you are allowed to go home. Would that be ideal?
Depends on what you have next.
Like when you are free, you can just walk out the gates and go where you want to.
Yeah.
And when you have a class again, you watch your time. So in other words, no bells. Come and go as you want to, or go to the cafeteria. If a teacher is not here, you just go to the cafeteria and not come to class. Wouldn't that be ideal?
Yes.
Okay. So ideal means it's sometimes like airy-fairy. It's not going to happen. It's not ever going to be like that. It's like utopia. So when we look at the ideal gas law, this law says that all gases are the same. That is what this law is built on. It's ideal because it presumes that all the gases are the same. Question is, are they all the same? Albert? Are all gases the same?
I mean, they share similar structure and they have similar properties, but I believe they have different, like for example, amount of protons and electrons.
Okay, so they can be different in the number of protons and electrons. What would make them different as far as that? Can you give me an example of gases that would be different as far as that's concerned?
Water vapor and chlorine.
Water vapor and chlorine. Okay, so that's a good example. So if we're going to look at gases and we look at, for example, hydrogen gas, and we look at water, and we look at chlorine gas, are they really all the same? No, they're not all the same. So what makes them different? What makes them different? So he mentioned that they could have different protons and electrons, and that's very true. What else can make them different?
The properties their boiling points and melting points.
Their boiling points and melting points can be different. Why would they be different? Why would these...
The bonds, right?
Their bonds, what about their bonds?
For example, chlorine could be instantaneous dipoles, right? And H2O would be covalent.
Will chlorine and hydrogen form dipoles?
Yeah, Miss, you said instantaneous dipoles. Yeah.
So
one side is like
so what type of intermolecular forces would you get in chlorine and hydrogen gas?
chlorine, you've got covalent, very covalent bonds.
Okay, so the bonds are covalent bonds, are very weak. But what can you tell me about the intermolecular forces between them?
The London dispersion.
They are London dispersion forces, which are the weakest forces you can get.
Right?
Sorry?
Intra is covalent ionic.
So intermolecular forces are your London dispersion forces, your dipole forces, and your hydrogen bonds or your hydrogen forces. So you've he just mentioned gases here that are dispersion forces in them, like hydrogen and chlorine. So the forces of attraction between the gas particles in hydrogen and chlorine is going to be very different from the forces that you're going to see between the water molecules, for example, right? So what will happen in water molecules? Will they be stronger forces or weaker forces? Stronger forces. So that means we cannot presume that all gases are the same. Okay? So this is important. When you look at the ideal gas law, and I'm going to put it back up there because I want us to remember the law. There are two things that we can do here. We can make some assumptions. And then we can look at reality. Now, as far as IB is concerned and the type of questions you're going to get in the IB, it's important that you understand how to argue the gas laws out. So you must be able to look at the assumptions and say the assumptions are, for example, your ideal gas. It's your ideal gas theory. Assumptions are the ideal gas theory. What are we assuming about them? Reality is what's actually going to happen in reality. So one of the assumptions that we make about gases is that all collisions are elastic. That's an assumption. So what's the reality of my assumption? Well, the reality is the following. If you look at water, which is the example that he just mentioned, water vapor, and you will see that that's not going to happen. The collisions between water particles are going to be absolutely elastic. Why? So we can look at it as being sticky. If, for example, in chemistry, if we look at particles,
You said all collisions are elastic, and then you said
inelastic. Sorry, inelastic. They're definitely going to be inelastic collisions in water vapor particles. So,
What do you mean by inelastic?
okay, so inelastic means that when they collide, they are going to lose energy. Also, if they collide, they could stick together. Now, if you think about the intermolecular forces in water, and I'm going to call it IMF, intermolecular forces. The intermolecular force that we see here is going to be my hydrogen bonds, right? Which we know is the strongest intermolecular forces that we have. So we know that these particles, when they do collide with each other, they could either stick together for a little while and then they can separate. Do you understand? So this gas law assumes that all the collisions between particles are elastic. In reality, it's not going to be elastic. If we look, for example, at hydrogen gas, if we look at helium, if we look at chlorine, yes, they will be elastic. Do you understand?
Mr. Elastic actually means the capacity to stick to one another?
So elastic is if they do not stick together. So it's like if you think about playing pool or snooker, when the two balls hit each other, they just go in different directions. They immediately separate. They don't stick together at all. They will just change the direction in which they were moving, or one will be standing still and it will start moving. But in the case of gases, you need to imagine these balls are all moving, and when they hit each other, all they do is they just change direction in which they move. They don't lose any energy. If we look at light gases like hydrogen, helium, chlorine, oxygen, those gases are small particles, light gases. The forces between them are going to be what type of forces? What are the intermolecular forces? They are London dispersion. London dispersion forces. So can you see why you need to understand the intermolecular forces? Because now you're going to apply it here. So these London dispersion forces between them, they are very weak forces. Because they are weak forces of attraction, it means that these particles will collide with each other and the energy lost will be very small. It's so small you can ignore it. But in water particles, that will not be the case. Water particles will start sticking a little bit more to each other. They will collide with each other and some will stay together. Some will separate, some will go in different directions, but it's not going to be ideal. It's not going to be all elastic. Yes, Asha.
You said the hydrogen is elastic, but then when it collides with oxygen, would that make it inelastic?
No, if you put hydrogen and oxygen particles together in a container and they collide with each other, nothing will happen. The only time you're going to change that is you have to increase the pressure. So how can you increase the pressure if you put hydrogen and oxygen together? You have to reduce the volume. Well done. So you've got to think of everything in terms of the particle theory. If I put hydrogen and oxygen molecules into one container and the container is the same size, they will just collide with each other and go on their happy merry way. The only way that I'm going to get these hydrogen and oxygen particles to collide with each other and stick together is if I change the volume. So I want you to think of sticking. How can particles stick together? There's two ways in which particles can stick together. One is if they have strong intermolecular forces between them. That's one way. The second way that they can stick together is if I change the conditions that they're in. So in the case of small hydrogen gas molecules and oxygen molecules, the only way I can get them to stick together is if I make the space in which they are moving smaller. So I have to change the volume, and when I change the volume, I will increase the pressure. When I do that, I'm going to change the conditions. Okay, so that's the first one. The second assumption. Any questions? Okay, so the second assumption is that particles move all the time. So they are in motion all the time. They're constantly moving, and they move at random. So let's look at the reality. So for reality we need to think, are there times that these gas particles might not do that? Can you think of any condition that's going to prevent that? Okay, so now, in other words, when will they start sticking together? What would I need to do to get that effect? Yes, Farah?
They need to be solid. So that will they move from the solid?
Gases are never solids, they're gases.
Oh,
Okay? So they're not solids, no.
Can you freeze them?
Can I freeze gases?
No, you just change the state.
You just change state.
You can go from a solid carbon, you can go from carbon dioxide gas to a solid carbon dioxide,
It's not a gas anymore.
but then it's a solid.
Yeah.
Okay, so that's where she's coming in with, okay, so how do I make carbon dioxide a solid? How can a carbon dioxide gas?
Temperature.
Ah, well done. So Farah is correct. Gases can become solids. But as long as they are gases, they need to be at a certain temperature, right? So who said you changed the temperature? Omar.
Yeah. you
Well
can-
done.
The fire extinguisher, because if you collect the gas, if you put like something like
Mhm.
a little bag over it and you turn on the fire extinguisher, you get dry ice.
Okay, so that means you are changing the temperature. So particles move all the time. How can I get particles to stop moving? I can lower the temperature. I can lower the temperature of the system. What happens when you lower the temperature of gas particles? What will happen to how they move?
Energy reduces and they slow down.
So less energy and they slow down. So if they slow down, what's going to happen to them? They will be closer. They will be closer to each other. So what's going to happen to the collisions between them? Will they have less or more collisions if they're closer? Not really more. They won't really have more collisions because they're slower. But because they are slower, they're going to move closer, and that means they will start sticking. Energy. E stands for energy. So if you decrease the temperature, you decrease the energy, the particles slow down, they get closer to each other, they start sticking together, which means you cannot apply this gas law if they are at a very low temperature. When the temperature decreases and you have very low temperatures, this gas law is not going to work, because then the particles aren't ideal anymore. Okay? Any questions? When will the particles stop moving?
Absolute zero.
So at absolute zero,
Absolute zero is known as
the particles will stop moving. So that means at 0 degrees Kelvin.
Yeah, what's an example for the second? Like an example, real life example.
As a real life example is if you take carbon dioxide gas and you cool it down, it's going to become a solid. If you take water vapor and you cool it down, what's it going to become?
Liquid.
It's going to become a liquid. How does it become a liquid? Well, you cooling it down, it causes the particles to slow down in their movement. When they slow down, they start getting closer together until eventually they will start sticking together because they are so slow and they have so little energy. They will just stick together. So you'll have a phase change from being vapor or gas to liquid. Do you understand? So that means at low temperatures, the ideal gas law is not really going to work because now it's not a gas anymore.
Yes, but saying that if they slow down and they stick together means that it's going to take up less volume, which is not always true. Like when you freeze, well...
Yeah, that's a good point. That's a very good point. So water vapor takes up a lot of volume.
Yeah.
When you slow it down and you cool it down, it becomes a liquid. It takes up a certain volume then, but now you're looking at changing the phase of the liquid to the solid. When you cool it down even more, it becomes a solid. So yes, the volume of the water is going to increase. Why does it increase? Why does the volume of ice increase? Why is it more than when it was a liquid? So think of the particle theory to answer the question. It's a very good idea question, yes.
Because the particles are closer together.
It should increase.
So the particles are close together in solids too. But why is a liquid water, why has liquid water got a smaller volume than solid?
Smaller or larger volume?
It's got a smaller volume. Liquids, water in liquid form has a smaller volume than water in a solid form.
So I think because like when something is solid, the particles are together, but when it's liquid, more energy, so the distance between the particles increases.
So you are now not answering the question, because if it's a liquid and your particles are further apart, the volume of liquids, a liquid water, should be smaller or should be bigger than the volume of a solid water. But it's not. Solid water has a greater volume than liquid. You take water in a bottle and you freeze it, the whole bottle expands because the volume increases. Does anybody know why? Nobody? So
Relate to thermodynamics.
Thermodynamics has got something to do with it. What? So what do you know about liquid particles? Why is it a liquid? How do they move? They slide over each other, but there's quite a lot of movement. But they're in touch with each other, but there's no specific arrangement in the water molecule, right? So the water molecules are in the water, they're free to move, and they slide over each other. When water freezes,
Is it because it has like a certain structure?
it has an absolute crystalline solid structure. So what happens is the intermolecular forces between them actually increases, but because the particles are arranged in a fixed pattern, they end up taking more space, they become less dense. So that's why ice always floats on top of the water. So the density of the water changes. And because the density changes, it takes up a greater volume. And the reason the density changes is that liquid particles have random movement, so the volume can be less, and solid particles, water particles, is going to have a more of a structure, and that takes up more volume. Right, now, the third assumption. So, we are still busy with assumptions and reality. The third assumption that we make with regards to this gas law is that gases have no volume. So in the ideal gas law, they presume that gases do not have a fixed volume. Remember when we looked at the particle theory, we said gases don't have a fixed volume. They will simply take up a whole container. You put them in a big container, they fill the container. You put them in a small container, it fills the container. Which means gases do not have a specific volume. So as long as it doesn't have a specific volume, we can apply this. Now, in reality, this is not true. When will this happen? So, in other words, if I increase the pressure, I will have volume. Because the particles will move closer together. So if I increase the pressure, I will have volume. Why? Particles
Move closer together.
are closer. If they are closer, I have an increase in intermolecular forces. If I have increase in intermolecular forces, it means particles will start sticking together. Right? A second way in which I can have volume is if I decrease what? The temperature. So we've just discussed it. So if I decrease the temperature, what is going to happen?
Oh yeah,
I will have volume.
more volume.
Why will I have volume?
There'll be a
Again, particles closer to each other. I will increase the intermolecular forces. Especially if you have water vapor and you let them cool them down, they get closer together, it's going to change to liquid. And when you have liquid, you have volume. So again, the ideal gas law, in other words, is not going to work when these two conditions are applied. When you increase the pressure, when you have high pressures, and when you have low temperatures. Okay? So you need to be able to discuss why the ideal gas law does not apply to all the gases in reality. So it's like comparing the ideal gas law with real gases. Yes.
But why do we use real gas law? Ideal gas law.
Because we can take this ideal gas law and we can apply it to just about any calculation that we get related to gases. This law can be applied and it can work, and it's easy to apply it to calculations. But you need to understand that in reality, this will not always work. The ideal gas law is based on assumptions about gases. Yes.
So how would that question look like? They would try to tell you use the ideal gas law, but then they say, oh my God.
You would have to discuss why can that law not always be applied. Okay? There is one more assumption. The fourth assumption is that there are zero forces of attraction and repulsion. So now again, we've already discussed what is the reality. The reality is when you increase the temperature and when you increase pressure, if you increase the pressure or you decrease the temperature, then this is not going to be true. Only if you have low pressures and high temperatures will this actually be true. Okay?
So if they're closer together by more pressure or decreasing temperature, they'll create forces of attraction.
That's it. Okay. Now, last one. And then I'll stop. Then I'll stop the lesson. And then you can do whatever you want to. So I noticed in your tests, which you will get back only on Sunday, that many of you were struggling to answer questions related to the calculation of stoichiometry. So I want to show you the ABC method. The ABC method of doing stoichiometric calculations. I'm going to use a very simple example. I'm going to use the following equation. Let's put it in a different color. So we'll just use the one for if hydrogen reacts with oxygen under high pressure. And I need to complete the reaction. What is going to happen? I take hydrogen and oxygen gas, I put it into a container under extremely high pressure. What's going to be my reaction? A synthesis reaction, a combustion reaction. If I burn hydrogen in oxygen gas, these are both gases, then I can have combustion. I can also increase them and put them under pressure and I'll get the same outcome. Okay? So this could be a combustion reaction, but it could also be synthesis if I just increase the pressure. What is my product?
H2O2.
I then need to balance this equation, which means I'm going to need 2 moles of hydrogen for 1 mole of oxygen and to produce 2 moles of water. So let's look at an example of a question for limiting reactants. So I'm going to do this. There are 3 questions they can ask you in stoichiometry. 3. The first one is, which one, they give you 2 of these. So let's look at, give you an example question. 3.50 grams of hydrogen gas reacts with 40 grams of oxygen. So there's 3 possible questions they can ask you. A, to determine the limiting reactant. B, how much product. And C, what is left over. Those are the only 3 types of calculations they can ask. Yes, so.
What do you mean by question mark product? The amount of product?
So, A, the ABC method.
Oh, okay.
A, they can ask you which one's the limiting reactant. B, how much product is produced. C, what is left over and how much of it is left over. That's all. There's nothing more they can ask. So let me show you an easy way to do any of these calculations, no matter what they ask you. Okay, just want to get out of my chair. Okay, so let's write down the 2 things that they give you. So maybe I shouldn't have drawn it so far down, but in any case. So the first thing that they give you is they tell you that you have 3.50 grams of H2.
This is for AMS?
Yeah, for A. So forget about the questions. This is what they give you. So now the next one is, the next step that you do is, you need to put this into my number of moles. Okay? So if I put it into number of moles, I will know that 1 mole of H2 is going to be 2.02 grams of H2. See, I've got grams of H2 here, so I must have grams of H2 here. And I want to put my 3.5, my mass, into mole. So at the top I have to have how many moles of H2. This is what I have. How many moles is that? The third part is to look at ratio. In other words, what is it that I want to know? I want to know how many moles of water is going to form.
Mr.
So-
remember we did this last year.
Okay, so in other words, I look at this and I say, right, I'm going to have 2 mole of water for every 2 mole of hydrogen, right? And then once I know how many moles of water I'm going to have, I'm going to go and say, well, if I know how many moles of water I have, how many grams of water is that going to be? That's what I want to know. So this is mole of water, and I will use molar mass again to say, well, 1 mole of water is going to be equal to 18.02 grams of water, right? So I now eliminate, I've now sorted out my dimensional analysis. Grams of H2O here, grams of H2 there. Mole of H2 here, mole of H2 there. Mole of H2 here, mole of H2 there, which means my final answer is going to be how many grams of H2O do I have? And your answer is how much?
31.22.
31.22, and I need to use 3 significant figures, so it will be only 31.2, because my question is 3 sig figs, 1, 2, 3, and 1, 2, 3. So 31.2 grams of water is going to be produced. Right? So I've answered A, not yet, but have I answered B? Yes. Because now I know if I have so much water, I will produce 31.2 grams of so much hydrogen, I will get so many grams of water. Okay, so now let's forget about the hydrogen and we do the oxygen component.
How did you know you have to do hydrogen?
Because they told me how much hydrogen I have.
Yeah, but why did you
So I started with hydrogen. Now they're telling me I've got so much oxygen. So now I do the same thing for oxygen. So I say, okay, I've got 40.0 grams of O2. So I want you to do the same thing for oxygen. So in other words, now I need to go and work out what is my molar mass for oxygen. So I see that if I have 1 mole of oxygen, what's the molar mass of oxygen?
16. But 2 oxygen.
That's 32 grams of oxygen. Because it's O2. So it means 16 plus 16, right?
But in the periodic table it says 16.00. Shouldn't we write it 22.09?
It doesn't matter because my final answer is determined by this, determines the sig figs, not in between.
Oh, no.
Okay? So 32 grams of oxygen. Now I need to do my mole ratio. In other words, I want to know how many moles of water will I have if I know how many moles of oxygen I have. Right, so my moles of oxygen is 1 and my moles of water is 2. Then I have to get again at the last part my molar mass of water, which I know 18.02 grams of water is 1 mole of water. So that's going to give me an answer.
It's 45.05.
45? So 45.05, I need 1 sig fig. So 3 sig figs, so it's 45.1 gram of H2O. Now I've answered A. How can I find the answer for A here?
See which one you get less of.
So the smallest value is the hydrogen, right?
Yeah.
Hydrogen gives me 31.2 grams of water. 40 grams of oxygen gives me 45.1 gram, which means I'm going to run out of H2. So H2 is going to be my limiting reactant, and that means O2 is going to be my excess reactant. Now how do I figure out how much oxygen will I have left over? What do you do to do that?
45.1 minus.
No, you go 31.2. grams of H2O and you go back to
So you see how much
oxygen, right?
H, so it's going to be 31.2 and 45.1 minus 31.2.
Okay, so this is what you do. To get this answer, you say 1 minus the ratio of my products. And the ratio of your products, you put the small one on top, 31.2, and you put the big one at the bottom, 41.1. And then you multiply it by, you want to know how much oxygen is in excess, so you multiply that by the 40 grams of oxygen. That's going to tell you exactly how much oxygen you have left over. The 1 represents the 100% of water that you are producing. So you're actually taking this ratio to work out what percentage of the oxygen is being used. So if you have 31 over 45, you're going to get the ratio of oxygen that was used out of the 40 grams. So it's just easy maths. You take the 1 minus the ratio of these two, small on top, big at the bottom, multiplied by the excess reactant, and you get an answer. And what's that answer?
12.328.
12.3 grams. So if I go look at this question, I've now answered my A.
My B and my C.
There's my limiting reactant. I've answered my B because the limiting tells me how much product I have. And I've answered my C. It's how much oxygen is left over. Yes.
If you want to find the amount of product, you use the limiting.
If you want to find the amount of product produced,
Yeah.
there's your answer.
I know, but you use the limiting reactant one.
Of course, your limiting reactant is how much product you will have.
Okay.
So once you've done these two, you get any answer from that. Okay? Any questions?
So oxygen is far more